variables was found in a different manner. So primarily we have force of lift and force of drag. In the wind tunnel that was measured in pounds, we were able to find that using the lift and drag device. 1/2 density. Density is found by the ideal gas equation using temperature, which is mounted on the wind tunnel, compared to temperature in the overall room. Velocity similarly is an application of density through Bernoulli's equation. Therefore, we can find the overarching wind speed. What you'll find is that we wanted to compare these directly to the actual fan speed in hertz, more so than the Bernoulli calculated wind speed. The more important aspect of this project is developing and showing the difference between the lift and drag at the same values. And by using fan speed as opposed to calculated Bernoulli speed, we can reduce some potential calculable error, and therefore we can better show in a more easily digestible manner the actual differences in lift and drag and how it compares to what we would expect. And then finally, we have the area. This is projected area. Projected area is effectively if you were to shine a light in the direction that air is traveling over the wing, it would create a shadow on a back wall, and we are finding the area of that shadow. Because these are full-scale wings and they can be somewhat complicated to actually find the projected area of, we use SolidWorks similarly, where we catted these out, and using some SolidWorks techniques, we were able to basically create a virtual shadow, then find the area of it in order for us to calculate our coefficient of lift and drag. As you can see here, at a 0 degree incline, we have just about 7 inches squared for the Concorde wing, and just over 7 inches squared for the 707. Relatively similar, but at the scale, a 1/2 inch difference is quite sizable. With all this said, finally, it's time to look at some of the actual wind tunnel testing results and see how they compare to the actual expected values of the Concorde 707.
The first thing we wanted to look at was the baseline behavior between a single wing with the 4 different angles of attack that we chose. So here we have 2 graphs representing the lifting force and the drag force of the Boeing 707 wing. At 0 degrees, being represented by the red line, 5 degrees being represented by blue, 10 degrees represented by the green, and the magenta representing the -5. As we can see here, it's quite obvious that a higher angle of attack prevents an increase in drag, increases the amount of lift. What's interesting is from a 0 to a 5 degree increase, it's quite a massive change, but going from a 5 to a 10 actually rests right in between the 0 and the 5. When you're thinking about this, and this might be due to the fact that the wing already has an angle to it. You see that 7 degree incline. So we figured that there is an optimal angle of attack for this wing, and we can use this information to compare this with the Concorde, possibly even go beyond that and understand why one wing is more of a subsonic, one wing is more supersonic.
If I could say one last thing concerning our data, you may notice that at 0 degrees we have a couple more data points going further into the fan speed range. We did not push these wings to their absolute limit in terms of speed. Quite frankly, we were a little concerned about their structural integrity as we continued the testing. The wings ended up being fine. There was absolutely no oscillation except at the most extreme speeds at a 10 degree incline. But generally, we felt safer testing them at a 0 degree incline for more speed as there was less drag. And we see that the trend does continue in terms of both lift and drag.
Focusing on drag now, we can see that the 10 degree has quite a sharp downward trend, while the 0 and 5 degree tend to be a little higher. Interestingly, we can see that the magenta almost rests perfectly within the red line, which would be 0 degrees. This is pretty interesting. So you would expect that a downward angle would result in more drag, but we're not seeing this here. We're not sure if it's due to the design or the measurements that we've conducted, but it's quite an interesting trend that we've noticed when looking at it post-test. Now, continuing off from just the Boeing 707, comparing it to the Concorde directly, we can see a pretty obvious trend of a higher lifting force being applied with the Boeing than the Concorde. This is interesting because you would imagine that someone that isn't quite familiar with these wings, they would think, oh, well, the supersonic is good at faster speeds, why wouldn't it be good at slower speeds? This is direct evidence to conclude that a subsonic wing is more beneficial at slower speeds than a supersonic wing at slower speeds. You see a massive increase in lift. While looking at drag, it's about the same, but the Concorde does drop off slightly higher. Now, this could be due to the fact that they were both constructed slightly differently.
No, actually, it's because of the fact that we didn't discuss high-speed flows in the classroom, and things actually reversed themselves at the supersonic flows. There's a whole new area of physics that we actually have not talked about in fluids. Actually, high-speed compressible flow was actually taken out of the course this semester.
Oh.
Yeah, and actually because I mean, it's like magic or some. It's possessed. Okay, so strange things happen to the aerodynamic and physics when you go to supersonic. And so it's just a function of the physics that we just have not discussed, you know. And you're right. And what you're saying is the phenomenon of what happens between lift and drag, between subsonic flow and supersonic flow. It's a complete shift in terms of the actual physics that describes it. So, but go ahead.
Fair enough.
What you said was perfect.
Yeah.
Thank you, appreciate it.
Yeah.
We can see that in subsonic situations that our Boeing wing, that is a subsonic wing,
Right.
performs better than the Concorde.
Yes.
This continues at 5 degrees, where we can see an even larger displacement between the lift of the Boeing
Right.
and the Concorde, and even a sharper decline between the drag forces.